Good afternoon, all of you. What I discussed in the last class regarding multi-compartment models. Do you remember that? Multi-compartment models, right? So, what it is telling us? It is following two deposition processes, right? Two deposition processes. What are those? Distribution and elimination. Okay, based upon these deposition processes, we are going to derive the equations. So in this multi-compartment open model, first we learn about two compartment open models. So in these two compartment open models, the drug will be distributed between the central and the peripheral compartments. The process is a reversible process. So here we need to get two kinds of constants, that is K12 here and K21 here. So your central compartment is also considered as compartment 1. Your peripheral compartment is also considered as compartment 2. So from this compartment 1 to 2, here we can able to get two different types of constants. And from this central compartment, we are getting elimination. So that's why here the rate of constant is Ke, that is nothing but K123. This is our constant. So till this part I covered in the last class, and then we derived according to the mass balance equation. We derived half part of this two compartmental open model kinetics, right? So till this part I derived in the last class. So the continuation from the last class is, so here we will get xt value, that is of x0 minus xc minus of k13. So k13 is nothing but your elimination. So this we will get it as integration from 0 to t xc into dt. So you can substitute this xt value in the equation 2. What is our equation 2? This is our equation 2. Right? What we get in the previous equation. See here, the same equation 2 I have written here. So this xt value is substitute in this equation, this place. Okay. So then you will get the equation dxc by dt is equals k21. See here, k21 is same. Then here instead of xt I substituted x0 minus xc minus of k13, right? Then k13, then integration of 0 to t xc into dt. This is all of your xt value. Then it is minus k12 plus k13 into xc is the same. See here, this figure is same. So from this part we substituted as xt value, what we get it from the last equations. Then you have to differentiate with respect to the time. So we are always talking about the drug concentration should be traveled with respect to the time, right? So if you differentiate with respect to the time, you will get the equation like d square xc by dt square. Here some squares will came. Just observe the difference. D square xc by dt square is equals k21, and instead of writing x0 minus xc, x0 is initial plasma drug concentration of your drug at time 0, and xc is the not plasma drug concentration, x is amount of drug, right? So amount of the drug at time 0 and amount of the drug at time t. So here when we differentiate with respect to the time, this whole term will become 0. See the difference, x0 minus c, here it will becomes 0, and minus dxc by dt. Why we are writing dxc by dt here? Here we are differentiating the rate of change of drug concentration. See, when we differentiating with respect to the time of this above equation, here we are differentiating the rate of change, the rate of change of plasma drug concentration. So, whenever we will talk about this rate of change of plasma drug concentration, definitely we have to write dxc by dt. So, this x naught minus xc term will become 0 and minus of dxc by dt and minus of k13 into xc, and this integration part you are not considering here. Here, this integration part will be removed after differentiating this equation. See, what is the difference between this equation and this equation? X naught minus xc will become 0, and then minus, here we are writing extra dxc by dt because of we are going to calculate the rate of change of plasma drug concentration here, and minus K13 and XC. So dt is already there. So then this term will be same. See, K12 plus K13, and instead of writing XC, here we are writing dXC by dt. Okay, so it is very simple thing. What is the differences between the first equation and second equation? Then you will write it easy. Okay, then d square xc by dt square is equals, see, you just multiply this k21 with these terms, then you will get k21, this is 0, no? So k21 into 0, 0. Then k21 into dxc by dt minus k21 into k13 into xc. So you are going to multiply this k21 with this whole terms. Then you will get the equation like this. Then this is remains same. K12 plus k13 into dxc by dt. Then here the common thing is dxc by dt. Here we have dxc by dt and here we have dxc by dt. So we can extract this common thing. Then d square xc by dt square is equals, see, minus of k21 plus k12 plus k13. See, we are extracting these three terms. Why? Because these three terms are commonly having this dxc by dt. That is nothing but rate of change of plasma drug concentration. Then we are extracting these three kinds of rate constants with respect to the dxc by dt. Then minus k21 into k13 into xc remains same. When you put it on the paper, then you can able to get, otherwise you may not. Okay, then d square xc by dt square plus, here plus will came, see, k21 plus k12 k13 dxc by dt minus into minus plus k21 k13 xc is equals to 0. So you will get the final equation like this. Then let us define that this K21, K12 and K13 is A plus B. A plus B is, that is alpha plus beta. A plus B, that is of alpha plus beta, and K21 and K13 is AB, that is nothing but alpha beta. Here alpha is nothing but A and beta is nothing but B. Okay, in your Venkateshwarlu textbook, this is mentioned very clearly. So then you can assume that this whole term is A plus B and this whole term is AB. Why? Because here we have a multiplication and here we have a addition symbols. So that's why here we have A plus B. Then here A into B. That is nothing but alpha plus beta or alpha beta. Then the equations are, see, the equation is same, d square xc by dt square plus alpha plus beta into dxc by dt. In the previous equation, we have K12 plus K21 plus K13, right? So instead of this whole term, we can write it as alpha plus beta into dxc by dt, and plus we have K13 and K12, right? So here we have alpha beta into xc, that is equals to 0. So here instead of writing your constants, we are applying some hybrids. Those are nothing but alpha and beta. These are called as some hybrid constants. So above equation is in the form of quadratic equation. What is the quadratic equation here? Ax square plus bx plus c is equals to 0. So this equation is in the form of quadratic equation. That is nothing but this ax square plus bx plus c is equals to 0. So therefore the integration of above equation, this above equation you will get xc, that is xc is equals to a into e to the power of m1t. See, a into e to the power of minus m1 into t. You just write it like this. Okay. Then b e to the power of minus m2 t. So here we are getting two exponential forms. Exponential forms. In case of one compartment open model, we'll get only one exponential form. In case of two compartmental open model, here we can able to get two exponential form. Those are e to the power of minus m1 and mt. So from where we will get all these things? From this quadratic equation. When you integrate this above equation, you will, after getting so many steps, you will get this equation. You can directly remember this and this equations. Okay, so there is no derivation part in the textbooks. So then this m1 and m2 are the root of this quadratic equation. This m1 and m2 are the roots of the quadratic equations. So you can write it your m1 or m2 as c minus b plus or minus root of b square minus 4ac by 2a. This is all related to the mathematical equations. So when you written this m1 and m2, these should be considered as the roots of this above quadratic equation. Then you can write this m1 or m2 in this equation form. So after writing this equation, once again you will write this basic equation. So your m1 or m2 is equals to this minus b plus or minus root of b square minus 4ac by 2a. So then we have an equation d square xc by dt square, and then we have an hybrid rate constant. This alpha and beta are called as hybrid rate constants. Okay, your alpha and beta, or in some textbooks they mentioned as A and B, whatever it is. These two are same. Then you can apply your equation into this equation. See, all minus b plus or minus, right? So minus b is alpha plus beta. Plus or minus is remaining same. Then under root of b square, that is alpha plus beta whole square, minus 4ac, minus 4ab, sorry, minus 4ab. ab is nothing but alpha and beta divided by 2. Okay, here we don't have an a. We have only b. That is nothing but alpha plus beta is considered as a value, small a value. Then minus alpha is same, plus beta is same, plus or minus under root of alpha minus beta whole square. Then what about this 4 alpha beta? Where it went? See here. Minus 4 alpha beta. Here we have a root and divided by 2. We just consider up to this mark. Okay. So 2 to the 4. So here we have root. So this 2 and this root will get cancelled. Then something into 0 is becomes 0. So that's why here we don't have this term in this equation. Then this minus into plus is minus, right? So here you will get the equation like this. Then minus alpha, then minus beta plus alpha minus beta divided by 2. Then here your minus alpha, this is the plus alpha and this is minus alpha. 2 will get cancelled, minus and plus. Then you have 2 beta by 2. This is your final equation in two compartmental open model when you have to given the drug through IV bolus. IV bolus through two compartment open model, right? So then this is all equation can be derived on the basis of mass balance equation, and you have one more method to estimate the IV bolus administration of the drug to through two compartmental open model. This method is nothing but your method of residuals, MOR, method of residuals. Residual is nothing but remaining. Okay. So whenever they will ask you in your exam point of view, you can write either mass balance equation derivation or you can write this method of residual. These both will derive you that drug which can be given through IV bolus administration by one compartmental open model. Okay. So the here in case of method of residuals, here they are using that relationship of X is equals to VD into C. Here we are using volume of distribution and amount of the drug and plasma drug concentration of the drug. So here also same thing, central and peripheral. This is number 2 and this is number 1. And here we have an KE. See here. DCC. So you can write small d, capital C and small c divided by dt. So you can write like this is equals K21 into XP by VP minus K12 XC by VC minus KE into XC by VC. What do you mean by C here and what do you mean by P here? P is nothing but peripheral compartment, that is of compartment 2, and C is nothing but central compartment. So V is nothing but your volume. So what is the volume present in the central compartment and what is the volume present in the peripheral compartment? See, if you know the concept clearly here, you can write it very easily. This is telling you in case of peripheral compartment. So first, which constant will comes? K2. After that, K1. So see here. From peripheral to central, we are writing here. That is K2 to K1. That's why it is K21. Instead of remembering that blindly K21, K12, if you know the concept, definitely it is very easy to write, right? So here we are telling with respect to the peripheral compartment. Our peripheral compartment is compartment number 2. So here we will get K21 and XP by VP. So whenever you are telling the concentration, you can write it X is equals to VD into C, right? So C is equals to X by VD. So this equation is in the form of these equations. So K21 into XP. Here we are talking the amount of the drug will be present in the peripheral compartment. So that's why XP. XP is nothing but amount of drug in the C2. That is nothing but peripheral compartment minus VC. VC is nothing but the volume of central compartment. So here the drug is distributed from central to the peripheral, nothing but from 1 to 2. So our constant is 1 to 2 and XC. This is amount of the drug in the central compartment. After that, we have an elimination rate constant. So from which compartment we are able to get this elimination rate constant? We can able to get this Ke from the central compartment. That's why here you can write amount of the drug present in the central by volume of the drug in central. So this equation is very easy to write. So this is of X is amount of drug in the body at any time T remaining to be eliminated. C is concentration of drug in the plasma. VD is volume of distribution. XC and XCP are the amount of the drug in C1 and C2. VC and VP are apparent volume of these volumes of your C1 and C2 compartments. Then the rate of change in the peripheral compartment, the rate of change in the peripheral compartment is given by dCp by dt is equals K12cc minus K21cp. Okay, this is 1 and this is 2. So here we are calculating the rate of change in the peripheral compartment. Okay, so for that here we have a central and here we have a peripheral. So how the rate will be changed from central to the peripheral? Here we have two compartments in two compartmental open model. So our drug will get deposition processes from central to the peripheral first. So here the rate of change in the central compartment was happening first. So that's why K12 cc, that is central compartment concentration. So central compartment concentration of your drug. Okay. So K12 cc. Then we have K21 cp. So this K21 is talking about the concentration of peripheral. Here we are insisting K2 to 1. That is our drug is having deposition characteristics from 2 to 1. So that's why here we have a peripheral compartment. So then the next equation is dCp by dt is equals, see, here we are always talking about X is equals to VD into C. So this is our basic equation. You just remember that, right? So K12 into XC by VC. Here we have C, that is central. So that's why XC by VC minus of K21 XP by VP. See how simple this equation is? Then the integration of above equation, that is nothing but this equation. So when you integrate this equation with respect to the Cc and Cp, that means the concentration of drug in the central compartment, the concentration of drug in the peripheral compartment, you will get the equations like this. Here there is no derivation part is available. You can remember these equations. X naught by Vc, X naught by Vc in case of Cc, that is K21 minus alpha divided by beta minus alpha into e to the power of minus alpha t. See ma'am, here we are extracting our hybrid constants, what we will get in the mass balance equation. So here they have written directly the hybrid constants. Those are alpha and beta. So here we will get two exponential. One is with respect to the alpha t and other one is beta t. So K21 minus alpha divided by beta minus alpha plus K21 minus beta divided by alpha minus beta. So this is just reverse to this equation. Here we are writing beta minus alpha and here we are writing alpha minus beta. So the rate constant is K21 only in case of central compartment. So here we are talking, whenever we are talking about the rate of change in the drug concentration with respect to the central compartment, here we can able to get two hybrid rate constants. Okay. So then we have a plasma drug concentration here. Then this is x naught by v naught. This is x naught by vc, right? This is x naught by vp. And then here we have K21 divided by beta minus alpha e to the power of alpha t, and here K21 divided by alpha minus beta and e to the power of minus beta. Did you observe the change here? In case of peripheral compartment plasma drug concentration, here we don't have minus alpha and here we don't have minus beta. So the drug will be transported from the second compartment to the first compartment. The hybrid rate constants will become zero here. So that's why in case of in case of peripheral compartment drug concentration, we don't have this alpha and beta hybrid rate constants here. The two equations are same. Only thing is here no alpha and no beta. Instead of Cc, you can write Cp. Alpha, beta are the hybrid first order constants for rapid distribution phase and slow elimination phase. So here the drug is rapidly distributed out, but it is slowly eliminating out. Okay. So you can remember this integration of these two equations directly. The relation between the hybrid and the micro constants is given as alpha plus beta. These two are our hybrid rate constant, is equals K12 drug is following depositions from one compartment to two, that is central to peripheral, plus peripheral to central, plus elimination rate constants. And then alpha beta is K21, that is peripheral to central into elimination rate constant. So when you write the equation C is equals to alpha into e to the power of minus alpha t, beta into e to the power of minus beta t. Cc is distribution exponent. This is distribution exponent plus elimination exponent. See, simple thing you have to remember here like this. So here our elimination of drug will starts from this point, right? So this is the distribution phase. So in this distribution phase, you have to consider the rate constant as alpha. In this elimination phase, you have to consider your beta as the rate constant here. Then you can easily understood the concept. So here, what is the distribution exponent? Alpha e to the power of minus alpha t. And here we have an elimination exponent, that is b into e to the power of minus beta t. Very simple concept. Okay. A and B are hybrid constants for two exponents. These can be resolved by the graph method of residuals. Okay. So this equation is capital A and capital B, x naught by Vc, here also x naught by Vc. Okay. So this is in the case of alpha, that is nothing but your distribution phase, and this is in the case of beta, that is nothing but your elimination phase. So when we are considering the distribution phase, the rate hybrid constant is alpha, and the elimination phase, the rate hybrid constant as beta. Then the equations will becomes, okay, this is with respect to the alpha distribution phase, and this is with respect to the elimination phase. So these terms will be same. Here we are talking about alpha, so then we have a beta minus alpha. So here we are talking about beta, we have alpha minus beta. Okay, so this is the plasma drug concentration. C naught is the plasma drug concentration immediately after injection. That is nothing but after IV injection. So instead of this, we can call it as initial plasma drug concentrations. C naught is initial plasma drug concentrations. So instead of X naught by Vc, we can write directly C naught. But why? Because we have a equation like volume of distribution relationship. So X naught by Vc is C. That's what C naught is equals to K21 minus alpha by beta minus alpha. So the equation is same for this B hybrid constant also. So how the method of residuals will explains you this exponential forms. See ma'am, you will get a by exponential deposition curve. You will get a by exponential deposition curve. So whenever the term deposition will came here, you can able to remember two things. One is distribution, other one is elimination. Is it clear? Okay. So how you will get this by exponential deposition? See, the name itself indicating you in this equation, you can able to get two exponential forms. See, e to the power of minus alpha t is 1, e to the power of minus beta 2 is other one. So this is the distribution exponent and this is the elimination exponent. That's why this method of residuals is also called as by exponential deposition method. This curve will be obtained after IV bolus of a drug that fits into two compartmental open model, which can be resolved or which can be explained into its individual exponents by the method of residuals. Residual is nothing but the remaining amount or the remaining plasma drug concentration. Original meaning for this residual is remaining. So we are talking about in the sense of concentration or in the sense of amount of your drug. So that's why method of residual will explains you the two deposition curves after taking an IV bolus drug which will fits to your two compartmental open model. So the initial equation will be C is equals to A into e to the power of minus alpha t plus B into e to the power of minus beta t. From the graph, initial decline is due to distribution is more rapid. See, from your graph, so your distribution is rapid. Here we can able to get rapid distribution and slow elimination, right? Slow elimination. So from the graph, initial decline due to distribution, which is more rapid phenomena, and the terminal decline is due to elimination phase. In that case, the rate constants alpha is greater than beta. So what do you mean by alpha? Alpha is nothing but our distribution hybrid rate constant. Beta is nothing but our elimination hybrid rate constant. Here we have a rapid distribution phase and slow elimination phase. So at that particular rapid distribution and terminal decline is due to elimination. In such cases, your distribution is more than that of elimination. Hence, the whole term e to the power of alpha t, that is your distribution phase, approaches 0 much faster than e to the power of minus beta. Once this exponential form approaches 0, you can neglect that e to the power of minus alpha. Then you will get C, concentration of plasma drug concentration is equals B into e to the power of minus beta. Why? Because here the drugs will approaches the distribution phenomena more rapid. In that cases, the alpha hybrid rate constant will become 0. So we are neglecting to write here. Then we will get the equation like this. Then my question is, what is this arrow mark? So generally we have to write the arrow marks like this. This arrow mark point shows you it is moving forward. But here I have written it is towards backward. Why it is? This is nothing but the back extrapolated plasma drug concentration. Back extrapolated plasma drug concentration. C is our plasma drug concentration. You have to extrapolate the plasma drug concentration. That's what this is called, back extrapolated plasma drug concentration. So I will show you in the graph clearly. Okay. So when you convert this equation into logarithmic forms, you will get log C back extrapolated plasma drug concentration is equals log B is equals beta T divided by 2.303. So whenever your exponential form will comes like this, you have a value of 2.303. This thing we already know. So beta T divided by 2.303. A semi-log plot of C versus T. See ma, clearly it is very simple and very important. A semi-log plot. So here we can always consider our log values. So that's why we are taking a semi-log plot. In the semi-log plot, we can directly plot our logarithmic values. C versus T yields the terminal linear phase having the slope of minus beta 2.303. When you back extrapolate it to time 0, it yields the y-intercept and we have a t half of 0.693 by beta. Generally, we have an equation 0.693 by k. Instead of writing k, here we are writing b. Because we are ignoring the distribution phase, we are considering only the terminal elimination phase. The terminal elimination phase rate constant, hybrid rate constant is of beta. That's why T half is 0.693 by beta. Then the subtraction of extrapolated plasma concentration values of the elimination phase. See ma, this is CR. CR is nothing but residual. R stands for residual. Remaining plasma drug concentration is equals original plasma drug concentration minus back extrapolated plasma drug concentration. Whenever you will get a residual remaining plasma drug concentration, for that you need what is the original amount, then what concentration we will extrapolate. When you subtract these two parameters, you will get a residual concentration here. Then it is equals A into e to the power of minus alpha t. So here we are writing alpha t, that is distribution phase. So why we are writing distribution phase here, I will tell you while explaining the graph. So when you converting this equation into logarithmic form, log of CR is equals log of A minus alpha t by 2.303. So, see, in case of previous thing, we have considered only elimination phase. That time, your drug will be rapidly distributed out. But whenever you want this remaining plasma drug concentration, we need a distribution of your drug hybrid constant. So, here, that's why here we have written this A into e to the power of minus alpha t. So how the graph will be? This graph is very important. Just stay for 2 to 3 minutes. I will finish it. Okay. Seema, when you plot the graph on semi-logarithmic graph, okay, the values are, you just take the values of time on x-axis and the logarithmic concentration, plasma drug concentration values on y-axis. Log plasma drug concentrations on y-axis. Okay. First, you will get this dark line like this. So, in this part, here we are getting initial plasma drug concentration, right? So, generally, we have written it as C naught. This is nothing but 0 is nothing but initial. Firstly, initial plasma drug concentration. But here we are talking in the sense of logarithmic values. That's why it is log C naught. Okay, this point clear. Then here we have a true plasma drug concentration values. So why we will get this line Okay, we will get this line with the use of true plasma drug concentration values, that is original plasma drug. Okay, not a residual and not a back extrapolated concentration. Here we are using true plasma drug concentration values, then we will get the initial point as a log C naught value. Then after this original curve, see, after this original curve, we have to extrapolate this curve. Extrapolate. So at which point, how we will extrapolate this curve? At which point the curve is able to change its shape. See, up to this mark it is coming some flow. After this thing, after this point it is changing its flow. Then you can extrapolate from this point onwards. See here, this is a straight line. So from this point you can extrapolate this line. This is called as log B. Log B. Okay, this is nothing but elimination. This is telling us the elimination. Then after this log B values, we will extrapolate our log C naught values to this x-axis. From this y-axis to the x-axis, we will get a residual line. Residual line. This is what the residual line. So this is also looking like the same original curve, but here it is having direct straight line without any curvilinear plots. So see here, we are getting direct dotted lines here. No changes in the uh, no changes in the curve. We are getting direct straight line here. This is called as residual line. That is nothing but log CR values. So here CR is equal to C minus CR is equals C minus C bar. C is original plasma drug concentration. C bar is our back extrapolated plasma drug concentration. So when you subtract these two, we will get the residual line. Okay, residual plasma drug concentration. See, this is called back extrapolated terminal portion of elimination phase. Thus, that is nothing but log C values. So, when you want to read this plot, first you can draw the plot. According to that, you can read it. Okay. So first you will get the curve. When you plot the time versus log C values, you will get two true plasma concentration curve values. This is called log C values. Okay. After getting this, at which point the curve is changes its shape, you can extrapolate your plasma drug concentration like this. Here you can able to get log B values. That is nothing but terminal elimination phase. Okay, that is log B values. Then after getting this, from this original true plasma drug concentration values, we will get another straight line with respect to the y to the x-axis. This dotted line indicating us as a residual line curve. So at the starting point of this residual line curve, we call it as log A values. Log A is denoting us the distribution phase of the drug. So this is what the bi-exponential plasma concentration time curve by the method of residuals for a drug follows two compartmental kinetics on IV bolus administration. Okay, so this is about the method of